What is time? A deceptively simple question, yet it is the key to understanding relativity. It is also the reason my hair is going grey. When we describe motion, we do so as a function of time. 10 meters per second, 100 miles per hour. But the mathematical description of velocity is moot, unless we can define time. Is time universal? In other words, is there an audible tick-tock throughout the galaxy? A master clock, so to speak, forging ahead like Mozart's metronome? The answer, my friends, is no. Time is not absolute. In fact, for us believing physicists, the distinction between the past, present, and future is but a stubborn illusion. A lot to consider, I know. I know. But understanding time is essential to understanding relativity. Now, I want you all to close your eyes. Not to worry, I don't bite. But I am on the lookout for a new pen. Go on. Close your eyes. To truly grasp the idea of time, we must take a step back and ask, what is light? So journey with me to the sun. What is time?
Imagine a radio signal is sent from Earth at the speed of light to an astronaut A, 1 light minute away, or 60 times 186,000 miles away. Now also suppose the signal was sent at 12 o'clock Earth time. Then the signal would arrive at the astronaut A at 12:01, and upon arriving at A it would be reflected back to Earth and arrive back at 12:02. Surely all of this makes sense. But here's the thing. The Earth observer E doesn't really know when the signal arrived at astronaut A. Of course, the Earth observer E is convinced it arrived at 12:01, but there's no way to directly verify it. But now what happens if 2 eyewitnesses observe the signaling events? One might consider that these eyewitnesses measure the events differently in both time and space. So how could they be both different as well as both accurate? This is the start of what is called the Einstein transformation problem. When the Michelson-Morley experiment verified the speed of light is constant in all reference frames, Albert Einstein, under the advisement of Poincaré, reformulated the theory of relativity and created the theory of special relativity, which would in turn be used to correct Isaac Newton's equations of motion and reveal that both space and time are relative to an observer in motion and not something absolute. In 1905, physics was about to be turned on its head. What is time? Or better stated by Albert Einstein, what does it mean to say that 2 events have happened at the same time? Perhaps one other way to think about this question is that if something happens, like an event, and it is observed by 2 people, how are each person's answers to the where and when going to be related to each other? How will each observer record the event? Well, each observer would be given the same ruler and synchronized clock. Their measuring devices would be the same. And an observation would consist of giving a location and time measured for an event. So this is what we mean by an event: a location and a time. Imagine an assistant and an observer see a flash at a flash point F. And imagine the observer is a distance x away from the flash, and the assistant a distance y away from the flash. The total distance between the observer and the assistant being the distance L, so L is equal to x plus y. The flash event we can call the pair xt, and as recorded by the observer, x, to, and by the assistant, y, ta. So what can we deduce about the event x, t? In other words, given from the perspective of each observer, what time do they see the event happen in? Well, t sub 0, or to, I should say, is t minus x over c, c being the speed of light, and t sub a is t minus y over c, time being given as distance over rate. So now that we have an idea of how we can formulate this into a mathematical idea, we're going to have to use our imagination a little. So imagine a station master S at rest in the station train house. And now consider that an engineer, we'll call E, at the helm of a moving train, is moving at a speed v. At the instant that E passes S at the station, they are immediately synchronizing their clocks. Call this instant 0. Then as the train moves on, a nearby tree is struck by lightning at flashpoint F. Wait for it. Okay, so what we want to know is how the observers S and E witness the event and how the differences in their observations are related. Now suppose also that we position an assistant A to the left of the station house S at a distance A from the station manager, as well as a brakeman B riding in the last car of the train. Let's go to the chalkboard. Okay, in our setup here, the barred system represents the system in motion, as the moving train reference frame is governed by some functions of velocity. We will dictate their coordinates as a function f and a function g for x bar and t bar, the space and time locations measured by the moving observer. And for assistant A, they'll measure their time as t plus a difference that is measured from the event, as well as the brakeman B, t plus s bar, meaning the measured event plus a difference in the time that they measure it. Now we're going to make some substitutions here, and at the synchronized time, when the clocks are synchronized, when E passes S, x and x bar are the same, we'll call them 0, and t bar are the instant 0 as well. Now for the assistant A, the distance xa is a distance we called a, and the time measured by a is called s. X bar, the brakeman distance, is a bar, and the time that the brakeman measures is called s bar. It's the difference in the time of the event and the way that they measured it. Now, if we take a bar and s bar, the distances and the times, and write them as functions of a and s, and make a couple of substitutions here, we're going to be able to show that these functions are actually a pair of linear functions. So I'm just making a few substitutions here, if you can follow. And when we establish that a pair of functions are linear, we can then get the general form for what those functions will be, and then we can use some information about the system to solve for those functions. So here I'm just demonstrating that the functions are in fact linear functions. So if we can write a function in this following way, where we add the inputs, and it's the same thing as taking the sum of the outputs, then this is a linear function, more or less. That's a very loose way of defining what a linear function is, but suffice it to say, this shows that they are linear functions. And because they are linear functions, that means that we can write them in the following way. A constant times x plus a constant times t. Since they are both functions of x and t, the event, we can have now two linear functions with coefficients a, b, c, d that we need to determine. Now consider the fact that distance is equal to rate times time. And the absolute value of the distance x, we can call that rate times time, c times the absolute value of t, and the same thing for the barred system. And this is basically the statement of relativity, that the laws of physics should look the same in both systems. So what we do is we can reformulate this in the following two quadratic equations to get rid of the absolute value bars. So this is a statement of relativity here, with the c being the constant, the speed of light. And now since these two, the x bar and t bar, are linear functions of x and t, we have a pair of quadratic equations that have two linear factors in common. So we can sort of express this in the following way. In the barred system, in the motion system, the equation reads x barred squared minus c should be squared, t bar squared is equal to a function e of v multiplied by x squared minus c squared t squared, which is in the unbarred or rest system. And at the instant 0, when the clocks were synchronized, both x and x bar were at the same location, and t bar happened at the same time. And at that moment, we think about that snapshot as a velocity of 0, so we can set the barred system equal to the unbarred system and determine that at the velocity 0, that e function had a value of 1. Now, if that was from the rest perspective, and we take now the perspective of the engineer riding along the train, then according to the engineer riding along the train, they're the one at rest, and the station is moving away from them at a velocity negative v. And by interchanging the event x and t and x bar t bar, interchanging them in the equations and replacing v with negative v, we can start deducing what the general form for that function e of v, a function of velocity, is going to be equal to. And with a little bit more deduction here, we can find that e of v is equal to positive or negative 1. But because in our synchronization event it was equal to 1, we can assume that e of v will be equal to 1 in this equation, and therefore the condition that we must satisfy for special relativity is that the barred system is x squared bar minus c squared t squared bar is equal to the unbarred system x squared minus c squared t squared. This is what's really known as the fundamental law of special relativity, and it's changing Newton's laws by assuming that the speed of light is in fact a constant in both reference frames. So it gives them a connection to each other, and now that we have this sort of new formulated statement, we're going to put it to use. And we're going to solve for the coefficient. So here's the problem. Find all linear transformations of the form here such that we satisfy the special relativity condition, the barred equation with the equal to the unbarred equation. Now in this equation, the system of equations, if you can recognize it as such, We're going to make this substitution by letting y equal c times t, and y bar being c times t bar. And what that does is it changes our system of equation to that in terms of just x and y. And what that allows us to now do is sort of set up a system of equations as a set of matrices. So if we make this replacement, we can change our statement of special relativity to x bar squared minus y bar squared equals x squared minus y squared. That's the condition we have to satisfy to find the linear transformation that we're interested in with our given substitution. Now, expanding this quadratic out by replacing x bar and y bar, expanding out the quadratic there, we're going to get this, and from the coefficients of this expansion, we can relate that to x squared minus y squared, and find that the coefficient a squared minus f squared equals 1, ae minus fd is 0, and d squared minus e squared is equal to 1, because they have to match the coefficients of x squared minus y squared. And we can sort of play around with that middle equation there and make the ratio a over f, which is equal to d over e, equal to some constant k. And by doing that, we can just sort of make our equation a little bit nicer to work with. So we're going to make some new substitutions here. And so substituting a equals kf and d equals ke, we're going to see that two equations pop out of this that look almost identical. We get k squared minus 1 times f squared equals 1, and k squared minus 1 e squared equals 1. So we can set those two equations equal to each other, or discover that f squared is equal to e squared. So we're trying to determine some of these coefficients. And with that would also come a squared equals d squared. Now from that we can either deduce that a equals d and f equals e, or a equals negative d and f equals negative e. But if we take either one of those choices and replace them back into the other equations, we get a is equal to the square root of 1 plus f squared, which is the same as d, b is equal to c times e, or equal to c times f, and capital C is equal to f over c, which is the speed of light, that little c. So making that replacement in our system of equations, we now have our system of equations take on this form. Now in E's coordinate system, x bar equals 0 would read as follows. We'd plug x bar equals 0 into the equation, and now we get something that looks like this. From that, we can solve for x, and we get negative c times f over square root of 1 plus f squared times t, which would indicate that that part in front of the coefficient in front of t is the velocity of the train, since distance equals rate times time. So the velocity of the train is given by negative cf over the square root of 1 plus f squared. And reformulating this by solving f in terms of v, we get f is equal to negative v over the square root of c squared minus v squared. So that means that the square root of 1 plus f squared is really the speed of light c over square root of c squared minus v squared, or that can be rewritten as 1 over the square root of 1 minus v squared over c squared. And that term might seem familiar to you if you're familiar with the Lorentz transformation. Now writing this out in the x bar and t bar notations, in other words, resubstituting this value back into our system of equations, we can now write the event x bar, t bar as a function of x and t, the unbarred system, and also as a function of the velocity of the train. Alright, so now, since that factor of 1 over the square root of 1 minus v squared over c squared is very common in this, we're going to call that the function g of v, a function of the velocity, but we'll just call it g of v. And this is often given a designation of gamma for the Lorentz factor in many of the physics books. So x bar is a multiple g times x minus vt, and the t-bar system is g times negative v over c squared x plus t. And since g of v must be some real valued number, because we're dealing with real valued physics, that means that the velocity v must be less than or equal to c, which is just a statement that no observer or nothing with mass can move faster than the speed of light. The speed of light is the speed limit for the universe. So when we have this sort of stuff all figured out, we can now take this thought experiment a little bit further, and we can ask a question about how long a person at rest would measure the moving train to be, and how different would it be from someone on the train measuring how long the train would be. In other words, would there be a distance difference measured at rest versus in motion? And a more peculiar question is, how would the times that they record of these events differ? And what are the implications of that? So in our moving system, x bar is g of v times x minus vt, and t bar is g of v times negative v over c squared x plus t. These are the relativistic transformations for the system in motion and the event that they are measuring. So x and x bar were equal to 0, and t bar were both equal to 0 at the time and place where the clocks were synchronized. Now, time is equal to distance over rate, so if we let the time measured be the length of the train divided by the velocity of the train, and substituting that into the x bar system, when x is equal to 0, we get an x bar measured to be this. X bar is equal to plus or minus the function g times the length of the train. Now, if the absolute value of x bar is the length of our train L as measured by the engineer, in other words, the person who is moving, then to them, they're measuring the train at rest. Because they're moving with the train, L bar here is actually the rest measurement of the train. And L is the measurement that somebody standing outside, not moving with the train, would measure the train's length to be. So we can reformulate this with the rest length being called L sub 0, and this is the formula for correcting the length for something that is moving and the length is changing or shrinking in the direction of motion. This is called often the Lorentz contraction, for the person named Lorentz who discovered this about the transformation. And Einstein was very keen on using this. So this was one of the corrections to the idea that things are absolute. No, space can contract in the direction of motion. So now, if we let capital T be the time that a flare went off at the back of the train as soon as it passes the station, then we can sort of deduce here how long the train was. If at the very front of the train was the start time, this would be the end time, and you can use the difference in times to get an idea. So we can measure that there's a difference in time measured between the people at rest and the people on the moving train. And in fact, putting through the calculations here, it shows that the moving train time would be measured to be less than the train's time to pass the station from somebody at rest. And if we let T bar be restated as T sub 0 as a rest time, then the time measured for the train in motion would be given by this relativistic correction, where we divide by the square root of 1 minus v squared over c squared. This is referred to as time dilation in the theory of special relativity. The faster you move, the slower your timeline will be. And as a matter of fact, the experimental evidence for this is the only thing missing for people to believe that this theory really is true. That things do actually shrink in the direction of motion and that time does in fact slow for them. So experimental evidence came in the way of measuring elementary particles. You see, cosmic rays bombard the Earth on a daily basis. And when molecules of air are struck by cosmic rays, they produce collisions and elementary particles will rain down on the Earth. But elementary particles don't last very long. In fact, a particular elementary particle called a muon only has a lifespan of 2.2 microseconds. And this is produced at high speeds in the upper atmosphere when the cosmic rays actually collide with air molecules. Now, let's assume that the height of the atmosphere is 100 kilometers where it hits. What would be the minimum speed necessary for a muon to travel so that the time dilation allows it to survive the journey to the surface of the Earth? If it only lives for 2.2 microseconds, time dilation will have to stretch out its lifespan in order for it to make the 100-kilometer distance. So if we do a little calculation here and assume that the muon was traveling pretty close to the speed of light c, the time it would take for it to make that trip would be 333 microseconds, way longer than 2.2 microseconds of its lifetime. Now the time intervals 333 microseconds and 2 microseconds are related by the time dilation equation here, and that would indicate that the velocity necessary for that to happen would be approximately 0.999978 times c, the speed of light. So very, 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 very close to the speed of light. Now, how long of a height would the atmosphere appear to be to the muon, since it would be contracted in the direction of motion? If we put it through the length contraction calculation, we get 660 meters instead of 100 kilometers. So this proves that because the muon survives the trip, time dilation does in fact happen. Which leads to a very odd paradox. One about two twins born on Earth, and one that has an idea that they're going to travel to a star close to the speed of light. This is what's known as Einstein's twin paradox, and it begins by the idea of two people being born at the same time. So naturally, let's consider Alice and Bob, both of the same age, twins, and both have a ruler and clock. Clock's been synchronized on Earth. Now what Bob's going to do is Bob is going to take a trip on a rocket ship and fly away to a distant star at close to the speed of light. He's then going to quickly turn around and come right back to Earth. So now, a couple of things that we need to know about the situation. First is that let's suppose the star is about 12 light years away, and that the velocity he's going to be traveling is about 60% of the speed of light. So that would mean that it would take her brother, Alice's brother, Bob, 20 years to travel there, and another 20 years to travel back. So therefore Bob would be gone for a total of 40 years. That's traveling at the speed of light, 60% of the speed of light, multiplied by 20 years, that's 12 light years. Okay, so now, to confirm Bob makes it there, it'll take 20 years for him to get there, but then 12 years for the light to bounce back from that event, meaning that it would take Alice 32 years to finally confirm that Bob arrived at the star. But now, what's going on in the meantime where Bob is? You see, as Bob is traveling, his time is slowing down because he's traveling close to the speed of light. But 8 years later, since there's 32 years for her to see Bob reach the star, 8 years later would mean a total of 40 years, Bob would return back to Earth. Now, according to Bob, the distance traveled was contracted by a factor of 0.8, means that he traveled in his eyes 9.6 light years. Instead of 20 years to get to the star, Bob only measured 16 years to get to the star, for a total travel time of 32 years. You see, Alice aged 40 years on Earth, while her twin brother Bob returned 8 years younger than her. I bet Alice is kicking herself and wished that she was the one to go in the rocket. Anyway, that's special relativity, and I hope you enjoyed this video. Please hit that like, subscribe, and notification bell for more videos. And stay tuned for the next one.